All right, Introduction to Scalars and Vectors, Part 2. So, if you haven't had a chance to look at Part 1 yet, it may be to your advantage to take a look at Part 1. In Part 1, what we did was we introduced the term scalar and vectors, showed or gave some examples of where you may actually find them in physics and engineering. And also, we talked about the two different ways to represent vectors, and those two different ways were the polar and rectangular forms. So now in this video, where we're going to start off is how to convert between those two different forms. Okay, so if the angle is measured, let's say from the positive x-axis, the angle of the vector, all right, we may say that if we wanted to go from the polar form to the rectangular form, we can take the cosine of that angle and multiply that by r, or the magnitude of that angle, in order to get the x component of the vector uh, in the rectangular form. If we want to obtain the y component in rectangular form, we'll take the magnitude, which we represent here as r, times sine of the angle of the actual vector. And that will take us from, again, polar to rectangular. Now, let's say, for instance, that vector has been represented in rectangular form, and we want to take it to polar form. What we do is we take the x component of the rectangular form, square that. We'll take the y component of the rectangular form and square that. Add those two together, and then take the square root of that sum. And that will give us the magnitude, or what is represented here as r. If we want to find, let's say, theta in the polar form, and we're given the rectangular form, we can take the y component of the rectangular form, divide that by the x component of the rectangular form, and then take the inverse tangent of that quantity here in order to find the theta of the polar form. Okay, so what if, remember in that previous example, we said we're beginning, the angle was being measured from the positive x-axis. What if, for instance, we are told that the angle is being measured from the negative x-axis instead? For example, we have r being some vector a, okay, and we have theta. So in other words, we have that vector a there. We have theta represent the magnitude, or the measurement, pardon me, from the negative x-axis. Okay, so this is what we're talking about here. Again, the vector begins from the origin, or more specifically, its origin, and it goes to some point P here. And in this case, we're calling this vector A. All right. Its projection onto the y-axis, again, we'll represent that as AY. And its projection onto the x-axis, we represent that as A sub x. And we're measuring the angle here from the negative x-axis now. Okay. How do we actually now find our A sub x value and our A sub y value? All right. So if we want to do that, what we do is this. First of all, ignore the signs that you currently have on the vectors, okay, temporarily. Just ignore signs. Don't think about them, all right? And what you do is you take the A vector, the magnitude of the A vector, and you multiply that by cosine of theta, okay? And then you take these lines right here, means you're taking the magnitude of this. So all it means is no matter what you get here, you're going to make this positive, okay? So you're going to make this positive, and you let that be equal to A sub x, and we're just saying that that is the magnitude that we have here, okay? And then you can take the vector's length here, or magnitude, and multiply that by sine theta. We take the magnitude of whatever comes out there. So if it comes out to be negative, you make it positive. If it comes out to be positive, well, you just leave it positive. And we're going to say that that is equal to A sub y, okay, or its magnitude. Now that you've done that, now and only now do you actually consider, or you assign a sign based off of where the vector, what quadrant the vector is located in. Okay, so now if you remember, this vector here, this vector here is in quadrant number 2, if you remember from the first part. This vector here is in quadrant number 2, and in quadrant number 2, your x is negative. Okay, so because of that, whatever value you get here, okay, you're just going to drop a negative sign in the front. Remember, this is the magnitude, so you just remove any negative signs that you get from here, and you're just going to put a negative sign in front. And whatever you get for a sub y here, or the projection onto the y-axis, or the y component of the vector A, you're going to take the magnitude of that, and so that's going to come out to be positive. Again, remember, in this quadrant here, your x is negative and your y is positive, and that's why we have this listed this way, because this is going to come out to be positive, and no matter what value you get for this, you're going to take the magnitude of it and then put the negative sign in the front. Okay, so this is what you do if you have your theta here being measured from the negative x-axis. Okay, so what if now you are told that the angle is being measured from the negative y-axis? Okay, so example again, your vector r, or the magnitude r, we'll say is equal to a, and theta represents the measure from the negative y-axis here. Okay, so here you'll see what I'm talking about, where this is a vector. Okay, again, this is the vector, and this vector here is being measured again from the negative y-axis. So our projection, AY projection here, and this is our AX projection. So how do we actually now represent our AX and or A sub x, in other words, the x component and the y component of this vector here? Well, okay, again, ignore any signs, just temporarily ignore any signs. And this time, if you're looking for the x component, you're going to take a times sine of theta. Notice this is different. That's why I highlighted this in red, in order to find the x component. And for the y component, you're going to take a times cosine of theta. And once you've done that, only then now will you assign the negative values based off of whatever quadrant it's in. Okay, so let's go back here. So what that means then is that since we're in quadrant number 3 here, after we've already done this, we're going to put a minus sign onto both our x and y components, because both components are going to be negative if they're in this quadrant, or the vector is in this quadrant. Okay, okay, so now why is that? Well, we have to go back to good old SOHCAHTOA, SOHCAHTOA, to understand, and what I'm saying is to understand why this was actually changed. All right? All right, SOHCAHTOA. So remember that SOH stands for sine of theta is equal to the opposite over the hypotenuse. Cosine of theta is equal to adjacent over the hypotenuse, and that's what CAH stands for here. And tangent of the theta is equal to opposite over adjacent, and that's what the TOA stands for. Okay, so now let's take a look at this. Remember when we were measuring from the x-axis here, all right? What ended up happening was, if this is our theta, and for instance we wanted to find well, let's say this is our theta. The opposite side is opposite to theta here. The hypotenuse is the actual vector starting from the origin out to some point. And the adjacent side is a side here that touches the actual angle. Okay? If we're looking at this from the y-axis, in other words, our theta is being measured from our y-axis here, then this is our adjacent side, this is the opposite side, and this is the hypotenuse. The hypotenuse here again represented by the vector. What you'll notice is the opposite side here, when we're measuring from the y-axis, is actually equivalent to the projection onto the x-axis. So this opposite side is equal to the projection onto the x-axis. All right? While this projection here, if you go from looking at the theta or measuring the theta from the x-axis, the opposite side is a projection onto the y-axis. And so now you should start to see why we actually changed the sine and cosine in there. Or more specifically, let's roll back just a little bit, why we take sine in order to find this and we take cosine to find that. All right, so let's roll back forward. So here we are again. So that's why you ended up with that. So what this means then is that if we were to manipulate this equation right here and this equation right here, what you'll notice is that the y component for this one anyway, if we're measuring from the x-axis, the y component ends up being your opposite, which is equal to the hypotenuse sine of theta, and your x is equal to the adjacent, right, which is equal to the hypotenuse cosine of theta. Okay, and that's what you'll get in this case. However, because we flip this, okay, and our opposite side now is equal to the projection onto the x-axis, and our adjacent side, okay, it would end up being this here, then because of that, our x component, okay, is equal to the opposite side, which is the projection onto the x axis, is equal to the hypotenuse, pardon me, sine of theta, and y in this case is equal to the adjacent, which is equal to the hypotenuse cosine of theta. Okay, so that sort of explains that information there. Okay, now so let's look at multiplication and division of vectors. Now, when you're multiplying and dividing vectors, it's so much easier to do this stuff in polar form, and I'll show you why. Let's say you're given an example where you have a vector A, which is represented by r sub A angle theta sub A, and you have a vector B represented by pardon me, r sub B angle theta sub B. Okay, if I was to multiply the two of these together, what I simply do is I multiply the magnitudes and I just simply add the thetas. Okay, multiply the magnitudes, add the thetas. If I'm dividing, I will divide the magnitudes and I would subtract the thetas. Again, that's divide the magnitudes and subtract their thetas. Okay, let's say we're doing addition and subtraction of vectors. In this case, it's much easier to do this when they're in rectangular form. If you're given a vector and that vector A, you know that you have a sub x plus a sub y, and you know you have a, if you have b, then you have b sub x plus, which is equal to b sub x plus b sub y, right? So if you have a plus b, let's say, you're asked to add those two together, what you do is you take the x component of each of those vectors and you add those together. You take the y component of each of those vectors and you add those two together. Okay? What if you're asked to subtract the two of them, a minus b? Well, you take the x component of the two and you subtract them. You take the y component of 2 and you subtract those also, and that will give you your results. Okay? All right. Let's say you're given a vector and you want to multiply that by some given constant. An example of that, you're taking 5 and you're multiplying that to the vector A. In order to do that, okay, let's say A is equal to a sub x plus a sub y. You just multiply 5 times each of the coordinates, or pardon me, more of the projections. Okay, so it's 5 times a sub x plus 5 times a sub y, and that will be your answer for multiplying 5 times a. Okay, and if you have negative 5 and you multiply that here, what you'll end up with very similarly, negative 5 of a x, negative 5 of a y. All right, so in this video, we went through a little bit more about vectors, and this was part 2. If you want to find more information on vectors, you definitely can look at my YouTube channel, or you can check out my website for additional information. My website is www.clydeletsome.com. Again, that's www.clydeletsome.com.